Today's lesson is going to be about functions. And so functions are, something you've hopefully seen before, where you have like f of x um, equals x plus 2, like just something like that, where you have f of x and then you have some kind of like behavior about x, right? Or you could have like y being f of x. And so it's just this idea of like a function. Um, and so we're going to talk a little more formally about functions. And one way we're going to do that is we're going to talk about functions in terms of relations, because a function really is a type of relation, right? Because you have this pair x, y that you're going to get from your function, right? Or x and f of x. And so you can kind of think of that as like a relation, right? So if you have like your function f, you'll have like x, f, y, or something like that, right? And so you have like the pair, the input x and the output y as your relation. So as I said, a function f can just be thought of as a relation from set A to set B. But it's more specific. So it's not just any kind of relation, it has a specific requirement on it. And the idea is that every element in A needs to map to exactly one element in B. And so this is the kind of way you define this, right? And so we'll break down this mathematical definition of what I'm saying using my first order logic. But just think about this from a high level first. So every element in A, so you have a function f that's going to be starting in A, and it's going to be ending in set B, right? And so you're going to get your elements that you're going to be inputting into your function are going to be from A, and the elements you're going to be outputting are from B. And this is the kind of notation you might see right here too, is like this f colon, like where it starts and where it ends, and then this arrow in between. Okay, so we have, now we're gonna look at this statement and break it down. So it says for all A and A, there exists a B1 and B such that the pair AB1 is in F. So this is what I was talking about, right? Where we had like this pair XY, where like you could have like XFY, which another way of saying that is XY is in F, right? So like you have this relation F over this pair. But we're going to talk about it in terms of A and B1 now. But it's saying the same thing. So you have like little a in big A. And so for every little a, there should exist some B1 such that that pair A and B1 is in F, right? So in other words, you should have some type of like, if this is my input, this should be my output, right? That's what this basically is saying. So that's like that first part. For all inputs, there should be some type of output B1 corresponding, and it should be happening over F. It should be defined over F. And so, the example I gave before, like we have f of x is x plus 2, right? And so like if I input 1, right? So like that would make this a1, then that's f of 1 equals 1 plus 2, which gives me 3. So then my b1 would be 3. So that's the idea of just like trying to give you an idea of what it means by like this is my input and this is my output, and like this is my function. Okay, so that's what the first part's saying. It's just saying that for every input, there exists an output, and it's defined over this f. And now we have our logical conjunction, and this is a way you're going to see commonly how we want to express saying something is like it only exists once, or there is only one. Sometimes what you'll see is like for every B2 in B, if this pair AB2 is in F, then B2 must be B1. Like this must be the same thing, because there's not going to be like another B2 such that, right? Like there's not going to be another value like where AB2 is in F, like unless B2 equals B1. That's the only case, because there should only be one. there should only be like one value in here in this pair. And that's like this property when we're saying that like maps each A from A to exactly one element. And so that's what that's saying, is if there's a B2 that A is that like this pair AB2 is in F, then B2 is equal to B1, because we already know that A and B1 are in F. So that's one way you'll see it kind of commonly expressed mathematically, is something along the lines of like, if I'm trying to say there's only one, I might say like, if there is another one, then it's the same as the previous one. That's the only way there's going to be another one, if it's the same thing. That's just a common way you'll express it. And so that's going to be something valuable to know how to express when we're trying to kind of express more complex things later on in this course. So this is just going over what I just said. For all A in big A, there exists a B1 in B such that that pair is in F. So that's saying for all A, there exists a B1 such that F of A equals B1. And then this other property saying is if we can find a B2 such that F of A equals B2, then B1 equals B2, aka F of A can only have one result. So some things to note in this lesson. So as I said, a function is a relation, and it's over two sets, right? Because you have your input set and your output set. And so similarly to other relations, you just write that as a subset over the cross product, the Cartesian product of these two sets. Another thing to note is this notation I pointed out, which is you can sometimes just write it as like you have this function f, and it starts at in set A and it maps to elements in set B. And so you can say f maps A to B. And so using the notation we learned, you can also say something along the lines of for all A and B and B, if this pair AB is in F, so if this relation exists, then that means that B equals F of A, right? Because that's what we're saying, right? B is the output of putting A into our function. Now, this idea of using this like F of A or F of X notation, it only really makes sense if X pairs with only one Y. So like if if you do have the case where like F of X could equal more than one thing, in other words, if it's not a function, if you have like a relation that's not a function, so you could have something that's an input that could have multiple outputs. So like F of X equals the square root of 1, or the square root of X even. Well, you know that the square root of a number is really going to be like plus or minus that number, right? Like you're going to get a positive value and a negative value. So like the square root of 4 is going to be equal to plus or minus 2, right? And so the idea is like there's two possible values for this. So I can't really say like f of 4 equals 2, because that's like not really capturing the whole picture, because f of 4 also equals -2. So the idea is like it should be that like this notation should only really work, like this f of something equals something. You should only really use it if it's a function. And some other terminology that you might have heard before in previous math classes is A is the domain and B is the range, right? So this is where you're starting from, the elements that you're mapping from, that's the domain, and where you're mapping to is your range. And so again, like this is, where you would find like your X, right? And the range would be like where your Y is. So one thing we're going to formalize is this idea of composition. And so composition is just this idea of taking like two functions and like basically inputting one function into another function. So you have this notation of H equals G composed with F. And what that really means is that you're taking f of a and you're basically inputting that as an argument to G. So the output of f is going to be your input to G. So this is something we might have seen before. And so one important aspect of a composition is, so here I defined it where we have this set f or this function f that's going from set A to B, and G is going from set B to C. And so what does that mean? Is from A, right, that's going to be in our set A. F of A, since f maps to B, that's going to be in B. So what I'm inputting into G is going to be something in set B, which makes sense because that's what I'm saying here, right? B maps from G to C. So then G of f of A would be my result here, and so that would be something in C. And so that's just something to note, is that like this this range of f should match the domain of G. That's how I'm able to like input f into G. And so that's what I'm saying right here. The output of f has to be in the same set as the input for G. And so let's talk about an example for this. So I'm going to talk about the example of 1 over x. And so we'll define the domain and range of f as the integers. So again, I just noted that using this z notation that we commonly use. And so I'll just say f starts in integers and ends to the integer. So we'll be inputting an integer and we'll be outputting an integer. And so if I want to define, so f of x is just like f of x equals x. So it just gives me x back. G of x is going to be 1 over x. So I need to define the domain of G. And so that's basically like, what can this value be, right? Like, what can x be? That's going to be my domain. And so I know that like I can't have x equal to 0, right? Like I can't have x as 0 right here, because that would give me a 0 in the denominator. So I know that like x, whatever this like set is that G's coming from, it needs to be like something that doesn't include 0. So I just decided to say z plus. So this is gonna be the positive integers. This is a common notation you'll see. So this is just like integers with a plus sign. So that'll just be like, 1, 2, 3, all the way to infinity. And then so that's your positive integers. And so I did that just so that way, like, I don't have a 0 in my denominator. So now so again, we had f mapping from z. Now G, we had mapping from z plus. Now where is G ending up? Since I'm doing 1 over x, these aren't going to be whole numbers, right? So they're not going to be integers. This is going to be things like 1/2, 1/3, things like that. So those are going to be my rational numbers. And so that's why I put Q here for my rational numbers. So I have f mapping from the set of integers to the set of integers, and G mapping from the positive integers to Q. So the question is can I make a composition H where like I'm inputting f into G? So I'm saying like G of f of x. And so the answer is no, because f could return something that can't be input into G. So say I am inputting 0 into f, right? Which I'm allowed to do because f takes numbers from the input, from the integers. So if I'm taking a number for f, and I'm going to say f of 0, that's going to give me 0 because f of x equals x. So f of 0 equals 0. And then I'm going to input 0 into G. But I already said, like, I can't because G is only taking positive integers. So this is not possible. And like, you can see why, because I would get 1 over 0. So that would be bad. So we don't want to do that. So that's the idea, is that we can't make this composition because we're returning an integer here, but we're only taking positive integers here. So the idea is that like what f is returning is not corresponding to what G is taking in. So another thing I wanted to talk about is that functions can take more than one argument. And so this is the idea that we have like we can have tuples as our input. So a common example is, this like usually like you have as like z squared equals the square root, or sorry, z equals the square root of x squared plus y squared, something like that. And so for the Pythagorean theorem, like you have, two inputs and you get one output. And so if you're thinking about like how this maps, right, like you're actually taking an input from like from the real numbers times the real numbers, right, the Cartesian product, because you have two real numbers that you're inputting. And then you're going to be just returning one number. So that's why it's just going to map to the set of real numbers. And so that's just another like way you could represent it if like your function is mapping from like multiple sets, right? Because this is where x is coming from, this is where y is coming from, and then it's returning to just one element. So it's going to have just one. So it's just going to be just the set of real numbers is what it's mapping to. You also can apply functions to sets. And so basically some notation you might see is like this idea of f of like big X right here. And so all that's just saying is you're applying f of x to every element in X. You're just applying f to every element in your set. And basically the idea is that it should, leave you, if I'm mapping from X to Y, then you should end up with elements all in Y, right? So all of these elements, f of x, should be in Y. And so this also could be called the image of x under f. That's just some terminology that we use, is like if you're applying a function to every element of a set, that's the image of that set. And so also if I wanted to like think about the inverse, so I'm basically like, thinking about like the y's that I'm getting here, you could do that. You could say, so the inverse of f applied to y, right? Because y is the end. So, the inverse is just basically you're going in the other direction. So you're going from y to x. So the inverse of f applied to y is all x's in x such that f of x is in y. So that's just basically saying this is the set of inputs that you're going to be getting to this f of x. So this is called the pre-image of y under f. So another thing I wanted to talk about is this type of representation, because this is another way we could be representing, we represented relations this way. So you want to talk about them in terms of like functions by looking at these graph notations. You want to be able to like look at this representation and kind of say something about these relations. And this is also something we'll be practicing a little in our practice problem set on Thursday. But you have, say like you have your domain X and your range Y, and then these arrows are basically like your function, right? Your f. And so if I wanted to say something like f, so this is my f, right? Like this is my function f. I'm gonna change its color. So my function f is basically like these lines here, right? And so the idea is that I want to talk about like what is happening like from here to here. So f of a, b, c, d would just give me the set h, i, j, right? Because all these are just mapping to these three elements. There's nothing pointing to k, there's nothing pointing to g. So it's just mapping to like these three elements, h, i, j. And so similarly, if I wanted to say that the pre-image of my set, so f inverse of hij, that would give me my input a, b, c, d. And if I also just wanted to say something like, okay, g and k, like they don't have anything pointing to them, you could say that. So f inverse of gk is the empty set. And so one thing to think about too here is, okay, I have these things that like aren't even being touched. Is that okay? And like by my definition of a function, that's fine, because remember my definition of a function, I just said that like every element in here has to point to an element in here. So as long as all of these elements have arrows leaving from them, it's okay that not every element here has an arrow pointing to them. That's fine. It's just each of these have to have exactly one arrow coming from them, is basically what it means to be a function. And so let's just do a little more practice on like this idea of kind of mapping over different sets. And so I want to do an example with square roots because I think it kind of gets you thinking about those like inputs and what it really means and like the importance of defining the domain and range. And so just a reminder that a function f is a relation on A and B that maps each A from A to exactly one element in B. So is f of x equal to the square root of x a function? Well, it depends is the answer. So I showed an example previously in this talk that showed that, there are cases where f of x equal to square root of x is not a function. And but there could be some ways that you could define it such that it is a function. And really it just depends on how you're defining like this A and B, how you're defining your input and output. It really will determine whether or not the square root of x is a function. And so let me talk more about what that means. All right. So if A and B are both in the set of real numbers, then it's not going to be a function, right? Because we already said that like, and this is what I was talking about previously, where if you input like -1 into f, then you're getting the square root of -1, which is an imaginary number. And so that's not a real number. So this is like an example where like, okay, you're not getting like, you're not mapping to B, so it's not a function. We're not getting a result. This input that is from A is not giving us a result from B. Now the second question is, okay, what about if I say A is a set of positive real numbers? So this is getting rid of my imaginary numbers because now I'm not taking the square root of anything negative. And B is a real number. This is still not a function because, so remember that we had two properties for a function. So we had like that there exists, or let me change this color. So our first property that we had was, there should exist some type of B1 for all A, such that A B1 is an F, or I'm going to just write it like B1 equals F of A, right? And so in this case, and this should of course be in my B, and this should be in my A. And so this was my example, is I found like an A in my A of -1, but there does not exist a B in my set of real numbers that's equal to F of A, because B1 would be the square root of -1, and that doesn't exist in R. So that was my issue here, was I was violating that property of like, there should exist something in this second set that is the result of F of A. But remember, I had another property to be a function, and that's that it should only be mapping to one value. And so it was something like where it's if F of A equals B2, then B2 should equal B1. And so that's how I expressed it, but basically it was just saying that, there should only be one value. So it should only map to exactly one value. And so if I put like 4 as my input, which is from my set of positive integers or positive real numbers, I'm still going to get the answer plus or minus 2, right? So the square root of 4 can be positive 2 or minus 2. So that's going to be two different outputs, right? You have a B1 equal to positive 2, and you have a B2 equal to -2. And so that's violating that second property, that a function can map to only one answer. So the question is like, can I tighten this to make it where I do have a function? And so I can say A is the set of positive real numbers and B is the set of positive real numbers. And so now I'm saying like, if I'm just mapping to like from, so like my input of 4, now the square root of 4, the only possible answer is positive 2. That's going to exist in R plus. So there is an answer that exists in R plus, and there's only one answer that exists in R plus. So in other words, negative 2 is not in R plus, so we don't have to worry about that now. And we'll get more practice with this. But this is just the basic idea of how, like, it does kind of depend on how you define your domain and your range on whether or not something's a function. Now, another thing I want to talk about is this is just the same definition I previously showed of a function. And so the full name for this is actually a total function. And so I do want to kind of specify that difference. So it's actually called a total function if it does follow these properties, where like for every a, there's a b that f of a equals b, and there's only one b. There's exactly one b. But there's also this idea of a partial function. And so a partial function still has that property where there's only one answer, like if there is like if f of a equals b1, then like it only equals b1. There can't be another value. But not every input needs to have an output. So not every element in A needs to have some element in B that is the output. And the reason I want to kind of talk about this idea of a partial function is that like the programs we write on our computer, these are really partial functions because they're really dependent on like certain inputs. But we have this kind of like larger set of inputs we could give in our computer, but like sometimes, you know, they only work for very specific inputs, right? Like if I'm writing something that only takes, you know, integers and I input a string, then I, you know, will not get an output. I'll get an error, or it might crash or something like that. And so this is just this idea of like the difference between a total function and a partial function is that a partial function still has that behavior where like there's only one result or a like two output, but it doesn't necessarily have to have an output. Now, some properties that we're going to learn. The first, these are things you also might have seen in previous math classes. And this is the idea of the first one I want to talk about is an injection, or something you might have seen more commonly as one-to-one. And so, you know, that those are the same, those are kind of, you know, interchangeable terms. I mostly use the term injection because I just think one-to-one is a little more confusing. But you can, you know, call it either way. And so I'm going to talk about these definitions of like what an injection is, because if I want to show something's an injection, it's always good to just go back to like a logical definition. And so if I were just to say this logically, for all x1, x2, and a, if f of x1 equals f of x2, then x1 equals x2. So this is this idea that if you have like these two sets, A and B, every element in A should be pointing to exactly one element in B, and you're not going to have like two elements pointing to the same thing in B, right? So if these things are the same, then like these elements in A should be the same. So this is again like our way of saying, you know, only one of these exists. It's another like example of kind of using that way of saying things in fancy math terms. And so that's the idea, is that like everything in B should only have one arrow pointing to it, in other words. But it can't have more than one arrow pointing to it. And so you could also say it like, you know, logically, you also could say it using like non-equivalence, right? If I like were to negate it and flip it. So for all x1, x2, and a, if x1 does not equal x2, then f of x1 should not equal x2. So if these are not the same points, then they should not be pointing to the same thing, right? So it's saying the same thing, just kind of flipping it around. And so, by definition, all functions map one input to one output. And so that's why I don't love like this term one to one. I think it's like a little more nuanced than that. So that's why I tend to use this term injection. And so another thing you might have heard is so you have this idea of one to one or an injection, and on the other hand, you have this idea of a surjection. And so it's also could be called onto. And so the idea for onto, so you could see by this like logical definition, for every element in B, there exists an element of in A such that f of x gives you that element in B. So in other words, like every element in B, so again, you have your A and your B, and every element in B should be hit by an arrow. Here, let me do it this way. So like you can have, so it doesn't necessarily have to be one to one. So you could have like multiple things pointing to one, but like you can have multiple arrows pointing to one element in B. That's fine because it doesn't have to be one to one, but to be onto, every element in B should be hit by an arrow. So if this like is more helpful, like this kind of visualization, like every element in B should be hit by an arrow. That's a fine way to like think about it. Similarly to like A, like no elements in A should be pointing to the same thing in B. Like that's for your one-to-one definition. That's fine too. So it's just really whichever definition, like if this more like hard-coded, like logical definition makes more sense, you can always go back to that. But like part of what you're going to have to be doing is kind of making an argument. Like if you're given this some f of x, like I might say, okay, is this a surjection? Is this an injection? And like explain why. And so, this is kind of the reasoning behind it, but often you might like want to go back to these more like formal terms for injections and surjections. So it's always good to just have those like, and you're allowed to use notes for your quizzes and assignments and things like that. So it's always good to just have these kind of definitions with you. And like, if you have to prove, like if I'm saying like, explain to me why something's a surjection, it's always a good start to just write down the logical argument. Like, this is what the definition of surjection is. And that's always a good place to start. And it will often give you partial credit as well. So that's always good too. And so with this idea of injection and surjection, if something is both an injection and surjection, then it is actually called a bijection. And so that's what this expression is saying is for all B and B, there exists an A1 and A such that f of A1 is B. So this is basically like you're onto, right? Like every B has an element such that it maps to that. And for all A2 and A, if f of A2 equals B, then A2 should be A1, right? So this is my way of saying that like only one thing in A should be mapping to something in B. The last concept I want to talk about is this idea called a pigeonhole principle. And this did somehow, I guess, came from people who used carrier pigeons or something. And so they had, these kind of like little boxes where they stored pigeons. And the idea is that if you have n boxes for pigeons, you can only store n pigeons. You cannot store n plus one. So if you have, in other words, if you have n plus one pigeons and only n boxes, that means one pigeon's not going to have a box. Or two pigeons are going to have to share. And so this seems like very very simple, but it has actually some pretty cool like mathematical implications that I do want to talk about. So we can think about it in terms of functions. So if we're mapping a function from A to B, and the size of A is bigger than the size of B, then there's not going to be any way to map every element in A to an element of B without them hitting the same element in B. So this is our idea of like, if the size of A is bigger than the size of B, you can't have this idea of one-to-one because you're gonna have like, right? Like if these are my pigeons, like very literally, you can think about this as my pigeons. like A is the pigeons and B is the holes, then like you're going to have two pigeons sharing one hole. So the idea is that like if the size of A is bigger than the size of B, this is what we're saying here, then you're going to have like two arrows pointing to the same thing from A to B. So that's kind of like an interesting, mathematical implication of this pigeonhole principle. And we're going to do some more examples of it that are maybe a little more literal. So another thing I could use the pigeonhole principle to say is an airport with 1,500 landings a day must be able to accommodate two planes landing in the same minute. So why would this be? So I want to think about how many minutes I have in a day and how many planes I have landing. And if I have more planes landing than I have minutes, then like more, then we're going to have some planes landing in the same minute. So we have 1,440 minutes a day. And so by the pigeonhole principle, that means that if you're having 1,500 landings, like I said, some planes are going to have to land at the same time. And so this also can be like done to kind of express something a little more numerically or more complicated. And so this is a more complicated word problem, but it's saying in a class of 35 students, if a majority are women and that a majority are majoring in computer science, then at least one person is both a woman and majoring in computer science. And so why is this true? And so I'm going to show you with this idea called a proof by contradiction, basically showing like you're going to assume that this isn't the case, that like this statement that I'm trying to prove is correct. I'm actually going to say, you know what, let's assume it's false. And we're going to like operate as if this isn't true. And then we're going to show that it's going to get us to like some kind of like logical contradiction. And so like, okay, no, so this has to be true. This is a very common type of proof, and we'll talk more about it once we get into more formal like proving things. But this is just kind of an example of like how you could use the pigeonhole principle with this proof by contradiction. So what you want to do is you want to kind of like formalize this a little bit first. So you say S is the set of all students, right? M is the set of all CS majors, and W is the set of all women. And so obviously the CS majors are going to be in a subset of S, and similarly the women are going to be a subset of S, right? Because the set of all students, that's going to be our 35 students that we mentioned here. And so if I'm saying a majority of women, of them are women, that means that at least 18 of them are women, right? Because we divide it by 2, and we're going to say like at least more than half of them are women. So that means that if, half is going to be 17.5, that means that more than half are women. So we'll say 18 at least are women. And I also say a majority of them are majoring in computer science. So that means that, again, at least 18 of them are majoring in computer science. And so if, again, like we had M as a subset of the set of students, so this is our majors, and the women as a subset of that like set of 35 students, then the union of them is also a subset of the students, right? So the union of them should also still be within those 35 students. So if they're a subset, then their size, right? Like this is what I'm saying is like the amount of people in this union should be less than or equal to the amount of students in this whole set of students. If they're both subsets and we union them, we can't get more than like what's in this set. And this is kind of the idea of that pigeonhole principle too. And so this is my negation, where this is where I'm going to actually like contradict my thing, like say something is false and then prove it's wrong. And so I'm going to assume that this statement above that like at least one person is both is false. I'm going to say no one is both a woman and a computer science major. So that can say like the intersection of these two sets is the empty set. Well, if the intersection of things of these are the empty set, we talked about this in our sets example, but that means the union is just going to be the size of both sets. The size of the union is going to be the size of both sets. And we already said that the size of both sets is at least 18. So the size of the union is going to be at least 36. But we just said that we have 35 students in the class, yet we have this set of 36 students. So that gives us a contradiction, right? Like there's no way we don't have enough students in the class for this to be true. So this gives us our contradiction, right? This doesn't make sense because the size of the union of the subset should be less than or equal to the size of the set. And so this gives us our contradiction and shows that at least one of these students is both a woman and a computer science major. You also can apply the pigeonhole principle to say more interesting things about functions. And this is the last example I'm going to give, but this is a really interesting example, and it's going to lead to a concept that you do need to know. So first, I just want to think about this idea of like mapping and sizes, like using the pigeonhole principle like we were talking about before. So if remember, if I'm mapping from A to B and A is bigger than B, then there's no way to map every element in A without two of them hitting the same element in B. And so an injection means that each element of B is hit by at most one element of A. So if A is greater than B, then by definition, F is not an injection, right? That's what we were saying before. There could be too many arrows coming from A. So for A to be an injection, A cannot be bigger than B. Well, for a surjection, it's saying each element of B is hit by at least one element in A. But if B is bigger than A, right? So a surjection is like if you have A and B, then every element of B should be hit by an element of A, however you want to do it. But if you have like more elements in B than you have in A, then you're going to have like one element in B at least not getting hit by an arrow. So this is the idea that if B is bigger than A, it can't be a surjection. So again, if A is bigger than B, we can't have an injection, and if B is bigger than A, we can't have a surjection. So what that means is for it to be both an injection and a surjection, they have to be the same size. So A has to equal B if I want it to be both an injection and a surjection. That's the only way that like both of these things cannot be true, is they have to equal each other. So this is actually like a really common property in math, that if a function mapping from A to B is a bijection, then that means that the size of A and the size of B are actually the same. So if you have a bijection, so I'm going to reiterate this because this is actually going to be kind of mind-blowing, like the things you can conclude about this. So if F is a bijection from A to B, if this exists, then that means that A and B are the same size. And so I want us to kind of think about the implications of that. And I think this is the part where it's like, wow. So again, this is just that property. If A to B is a bijection, this function F is a bijection, then the size of A is the same as the size of B. Well, think about that if A and B are infinite sets. So if A is the set of natural numbers, right? So remember that our set of natural numbers was like, that's just going to be 0, 1, 2, 3. And and B is a set of integers. B is going to be like -3, -2, -1, 0, 1, 2, 3, and so on. So B is going to be in Z, and A is going to be in the set of natural numbers. And then I could show some type of F that maps from N to Z that is a bijection. So say I define some bijection F that starts from the set of natural numbers and ends in the set of integers, then that means the set of the natural numbers is the same size as the set of integers. So again, like this set I was talking about of like 0, 1, 2, 3, and this set of like -3, -2, -1, 0, 1, 2, 3. This is saying that these are the same size. These two sets are the same size, which is like, what? How is that possible? But that is the implication of this principle. And this is The theory behind this is that these are the same size. And so you might have heard about this before, where it's like you have infinities of different sizes or infinities of the same size. And so that's what this kind of comes from, is like these are infinite sets, but they're the same size. And so you can do this. So try at home, coming up with a function that's a bijection that maps from the set of natural numbers to the set of integers. And so if you can do this, if you can come up with this bijection, this set is called countably infinite. And so this is a common thing you also hear in math classes, this idea of being countable. And that just means that you can basically map from one set to that set, basically like if you can map from the natural, if you can map from the natural numbers to that set, using a bijection, then that set is considered countably infinite. In other words, we can kind of somewhat have an idea of the size of that infinity because we know it's the same as the size of natural numbers. And so this is the idea of something being countable, is another way you might often hear it, just saying something is countable. And this is how that definition works. So this is how basically, if you were to define this bijection, this would be showing that the set of integers is countable. And so one final little concept that I did want to talk about, and I just wanted to introduce this because if you're continuing in the major, this is going to be a big part of the major. I'm not planning to quiz you on this or test you on this, but this is something you will be seeing, and so I want you to kind of be prepared for that. And so this is something that you might have had hinted at before in your other classes. But the idea is that some computers have size and memory limits, right? And so sometimes like you want to think about your algorithm, you want to design it intelligently so that it's not going to be like running forever, right? Or it's not going to take like 5 years to run, or it's not going to fill up your entire memory. And so there are ways to kind of like mathematically describe these algorithms so we can kind of make more guarantees about what they're doing. And so this is, again, like you'll learn this more in your later classes, but this is very important. You know, if you're going to be a computer programmer, you need to kind of say like, this program is at least this fast, or at least saves this much memory, especially if you're trying to argue that like my algorithm is an improvement on a previous algorithm. Like you want to be able to kind of, you know, formalize that and actually like quantify it. And so this is done using types of notation. And so it's called asymptotic notation. The most common one is big O. And so it's literally just like a big O. And it's used to measure the worst case scenario of an input. So this is like the worst possible input I could give to my algorithm, so the longest it can possibly go. So it's my upper bound to my input. And so this can be defined as this function. So like I'm going to say this is in, so my, like say this F is like my algorithm, it's in big O of G of N, then basically like this is going to be the upper bound. Like this is, F is going to be like the runtime. And so if my runtime is in big O of G of N, then that basically means that like this function is going to be the upper bound of like how large my algorithm can be in terms of time. And often we just kind of talk about it like in terms of a general N, where like N is the size of your input usually. And so the way you would kind of formally say this is there exists a C in R plus, and we'll talk about more what this is, but this is going to be some kind of constant. And it says a positive constant, and there exists an N in the set of natural numbers. And again, like this is just going to be like your bound of like the size of your input. So for all little n less than n, so like within this input limit, so the speed of your function, of your algorithm, is going to be greater than 0, right? It's not going to probably take no time, but it's going to be less than some constant times this function g of n. So this c just kind of gives us a little more wiggle room because it gives us that like constant. It gives this idea we can add a constant to the function, but The idea is that like in general, it'll be like this function g of n is going to kind of bound how our algorithm is going to run. Like that's how long it's going to take, no longer than g of n. You might also see this omega, and this is basically the kind of like the opposite, where it's measuring the best case scenario of an input. So in other words, it's the lower bound of your input. And so it has a very similar definition where you have a constant and you have like this like limited size input. But you'll see here now like f of n is bounded from below by this g of n. So basically like this function g of n is going to like describe the very fastest, like if you give it an ideal input, the very fastest your algorithm can run. This one's a lot less useful because you really like in the real world, you want to kind of think about these worst case scenarios. So that it's often like more common, much more common to use big O rather than big omega. And there's also this idea of theta. And it's basically used to describe a function that is both in big O and in omega. So if you can find like a function, and this kind of needs to be zoomed out a little, but if you can find a function that kind of sandwiches f of n, so you basically just have like two new constants now. So you'll have like one lower constant and one higher constant, and you basically like want g of n to kind of sandwich f of n. That's the idea of theta, is if you can define that g of n, then that means f is in theta of g of n. So that's just some very light intro to the idea of measuring sizes of inputs. Like I said, you'll learn more formally about how to do this in future classes. But I just wanted to like introduce it to you while we're talking about functions, because this is like something that's going to come up later in like not in this class, but in other courses. And so I really wanted you to be more comfortable with that.